Righty. Thank you. I'm here from U.S. Geological Survey. My co-author, Carl Shapiro, is on jury duty today, so he's not with us. But I'm a physical scientist by background, a geochemist, and Carl's an economist by background. So together we've begun to work to reach into this area of ecosystem services and valuation and work at how can we bring USGS science and biophysical science, our own, and certainly with partners, particularly like EPA and NOAA, bring it to bear to allow those things that typically haven't had a value to have more of a value, particularly in the discussion around trade-offs for natural resource management and land management. Let's see. Oops. Okay. U.S. Geological Survey is a science agency within U.S. Department of the Interior. We came out of the Lewis and Clark Corps of Discovery, looking at our mission of classification of public lands, determination of the geology, mineral resources, and what we call products of the national domain. And those products of the national domain is that broad umbrella for us of all of those things within nature that are ecosystem services. And we have our mission describing and understanding the earth, loss of life and property minimizing due to natural disasters and hazards, managing those resources, and enhancing quality of life. Here's a USGS Division of Science. We 2 years ago underwent a reorganization, a realignment, moving from 130 years as a discipline-based organization with an academic-type structure into an issue-based structure. And the ecosystem services issues cut across all of what we call our mission areas. This is the one Carl and I work in energy and minerals and environmental health. Just so that you wonder, okay, why would Department of the Interior? It certainly reminds one of Western lands, but we do have a lot of coastal and oceanic responsibilities, and I just wanted to read some of these. Department of the Interior is responsible for managing 35,000 miles of coastline. We have 1.8 billion acres that we're responsible for managing of the seabed, outer continental shelf for subsurface minerals. We have 177 island and coastal refuges. We have Fish and Wildlife refuge system within Department of the Interior. There are 74 marine or island parks. We have national parks and 92 million acres of coral reef ecosystems. So while you might see the buffalo on our logo and think onshore, Interior has a lot of role in coastal and marine oversight for the nation, and USGS brings unbiased science. We are not a regulatory, have no regulatory function, but we bring the science and the research to underpin Interior's land management responsibilities. I think it was Lydia talked about the value earlier of synthesis, and we are seeing that more and more. I've plotted usefulness of our science to decision makers, from less useful to more useful for decision making at a high level for land management, and the amount of synthesis and interpretive work that we have to do in biophysical sciences. We certainly do a lot of data collection and basic science, information and research, but we're moving up this value curve, doing more and more synthesis, producing information out of data to knowledge, and also to options and providing options. And we're trying to do this providing of options and optimization within an ecosystem services framework. So we're developing from basic core capabilities of science up this curve to develop the capacity, ourselves and with partners, to do more integration, to inform more and more complex trade-off type challenges. And we do this every day in the energy and minerals and environmental health mission area. Here I've shown on the left classic USGS core capabilities, such as, for example, energy and mineral appraisal. We do this for the nation and globally because our future supply, largely of minerals and to a great extent energy, are in the global for import. We have long-standing ability, economic models, and the ability to put these in a market appraisal and valuation system. Over the last 10 to 15 years, we've begun to bring in environmental impacts, particularly of energy and mineral and also water and other resources, and bring those to bear for a broader picture of environmental impact for resource appraisal, potential extraction scenarios, transport and use. And then most recently, kind of an emerging capability, we're bringing all of this science to bear in biophysical models and putting that in an ecosystem services framework to move towards the right, which is the emerging capability we hope to do. And that is these scenarios where we look at vulnerability and risk and optimization in complex natural resource and land management decisions. So core capability, building and taking what we know, particularly about economics and appraisals and services in the energy and mineral regime, and bring it into a broader look at biologic components and hydrologic components, which typically have not had a commodity or the ability to put a price. So we're taking those core capabilities and expanding them. As we move from the left to the right, the amount of synthesis has to go up, and certainly the partnership efforts have to go up, because we certainly cannot afford to do this alone, so the partnering aspects are critical. I'm going to talk about 3 stressors at a high level, sea level, that we're working on. Sea level rise, a host of environmental health ones, some of which certainly Paul's covered, so I'll hit those lightly, and then a natural hazards one. Just with some examples. Sea level rise certainly is one, a major stressor for coastal ecosystems. This is just a model that shows you static sea level rise. That's just the filling of the bathtub approach. Sea level goes up for San Francisco Bay, showing a scenario of here the existing San Francisco Bay bathymetry. Here you see a scenario around 1 meter sea level rise and what that would do to the bay community. So we run a lot of models, just use static. Again, filling of a bathtub, increase in sea level. Here again, one of the earlier speakers talked about coastal vulnerability with respect to sea level rise and these eustatic models. We're working with partners here looking at what is the risk for sea level rise in vulnerable coastal communities. So we provide this this was the first, it's an old map, but it was one of the first looks at national risk for coastal vulnerability. Some communities are much more vulnerable. Looks at a host of parameters to figure out kind of what is your risk. Is it high, medium, or low? So we take what we know, particularly for us from a geologic and geoscience perspective and a hydrologic perspective, and put them together into these high-level national and sometimes international assessment products. Here's one, again, moving some of this work into the international. USGS has some partnerships looking at some of the large deltas in the world, because when you look at vulnerability from the standpoint of coastal communities, deltas are hugely vulnerable for 2 reasons. They're largely around the world, huge population centers, and they're also the centers of major agriculture for food supply. So they're extremely vulnerable, and we partnered to work on our what we call our Dragon project, looking at risk and vulnerability for deltas around the world at a high level. Another is not just the eustatic sea level rise or filling of the bathtub model, but there's also active coastal erosion that make coastlines vulnerable. Here we're looking, I want to just show you an example. It's an extreme one from Alaska, the National Petroleum Reserve, Alaska. You are looking from the offshore to the west-southwest. This is a shoreline of the North Slope of Alaska. And we've monitored this through time, moving through 2001, where the shoreline was, 2003, 2004. And I want to draw your attention to this series here of wells that were drilled in the 70s in the Petroleum Reserve, sort of looking for oil potential. And the vulnerability, these were way onshore, safely located at the time they were drilled. The loss of sea ice due to general global warming has really ramped up the erosion rate. Look at this erosion rate, 13 meters per year erosion rate, meters from 2002 to 2007. Again, due to loss of Arctic ice. This is the everything's connected to everything else point, I think, that Paul made. So I'm going to take you there and show you what this looks like on the ground. This is about 1980. These are pilings. Here's the wellhead. BLM has ownership of this site. Now, here are the pilings that brought the infrastructure to service the wellhead, 1980. Here by 2004, the wellhead is still there, but this is the shoreline. This is the ocean on the north coast of Alaska, 2004. Here's 2005. The wellhead's gone. You had to type that out, and those are the pilings that are left. So extreme coastal erosion in extremely fragile shorelines and coastal areas is a real hotspot of research and a concern for coastlines. Again, we're looking at the complexity of this. For USGS, what we're trying to do is to take all of the science that we can bring to bear, integrate these. And shorelines and shoreline coastal vulnerability is complex. It's not just sea level rise. There's also the stability of the sediment, the compaction, the sources of sediment, how much roots you have to stabilize that soil. So it's both a vertical component and a lateral component as you look at most coastlines. And there's a whole host of drivers that affect this. And the overplay or underplay of any one of these drivers makes it become what in this workshop would be called a stressor for coastal vulnerability. And so it's not, you can't just look at one of these and solve the picture. You have to look at all of them and integrate them. And that's what we're trying to do for things such with partners. Again, NOAA and EPA are our two partners in working with this. And we're looking at these wetland vulnerability assessments. How vulnerable under different scenarios of change in sea level from, a millimeter to multiple millimeters are various aspects. This is an example of that assessment for the Mid-Atlantic. And you can see some areas are very vulnerable, shown in blue. Others are somewhat, shown in sort of maybe in red. And then the browns and tans are not as much. So again, trying to communicate, I think one of the questions was how do you communicate to the public some of these more complicated issues? And these assessment products, again, working with EPA, working with NOAA, to make these easier to visualize helps us communicate the importance, whereas maybe the general public might not appreciate looking at the guts of a biophysical model that describes this in certain scenarios. We would lose them for that. I want to look now at environmental health. I've got a host of those. I'll just give you a snippet of each one of those because this is a large part of what USGS as an environmental science agency does. Here's one on methylmercury. This is not yet published, but it's the first national map of methylmercury modeled occurrence in surface waters. Most of us realize that the source of mercury in the United States over the landmass such as this comes from deposition of ash from coal-fired power plants. But it's not the deposition of that ash that provides a concern about human or environmental health. It becomes toxic through methylation of the mercury, and that's biomediated. And so it's that combination of water, the microbes in the water, it's microbially mediated to get that toxicity. But what we're trying to do is to look at regions. Obviously, the arid Southwest is not as much a concern. So how, from a regional level in the United States, can we look at these potential issues, again, modeled, in this case, of methylmercury? We've just begun to move that into the coast and ocean environment. Here is a collaborative study that we're doing with academics and the U.S. Geological Survey. It's funded partly by NSF and NOAA on a cruise, and this is going from Honolulu, Hawaii up to Kodiak, Alaska. And what we're trying to do is to look at potential toxic mercury in the surface water and also the water column. And what we suspected is that there was a lot of movement of coal ash and so forth from the atmosphere and then into ocean waters, causing potential concerns about mercury in the Pacific Ocean. And this is our preliminary modeling results, and you can see again here's Alaska, and so here would be that transect, and we're seeing a large plume of concern of mercury levels in the oceans, and that mercury is coming through atmospheric deposition off of coal-fired power plants in China and Asia and moving into the water and being mobilized. Another environmental health are coastal processes due to movement of water around the coast and the interface, right? The interface of the land and the water with the weather and the movement is a sort of a hot zone for a lot of biological activity. And one of the things that we found, if we've learned one thing in the last 10 years, it's you can't look at one part of the system alone. You have to look at bird populations, the effects on water, and so forth, because what we're trying to do is to, again, work with partners to look at beach health. How can we come up with indicators quickly that translate into health of a beach, both for the wildlife, for people, and so forth, and look at these indicators right at this critical zone. And again, it's interdisciplinary science. And it's a difficult thing because you're translating across science culture, science practice, language, data. How do you collect your data? You know, QA, QC, integrity issues around data collection, QA, QC. So we are right at the tip of the spear of trying to come across all those cultures and practices in order to be able to do things like say, okay, what's the total picture for health? Because a citizen wants to know the beach health. They don't want to know the nuances of all the parameters and the uncertainties associated with those. A lot of work in disease in marine systems. Again, what we're finding is it isn't single components. I think Paul gave you a phenomenal list of chemicals and then things that can happen in organisms. We're finding that it's chemical mixtures and those types of things, daughter products that mix with daughter products, and getting a handle on chemical mixtures and their effects in the marine and other environments, freshwater environments, is a quantum leap forward in the science for these third, fourth, and fifth level order interactions. But that's where the science is going, and we're trying to take what we know about the basics and move that forward in understanding with respect to the marine ecosystems. Another environmental health, Paul talked about this one, ocean acidification. Again, working with partners there. We're trying to look and compare across a wide range of the ocean so we get a sense of what's the frame of the page. Because you can find a field area anywhere, sample it, and come up with whatever. What's the big picture for planet Earth? We're looking in the Caribbean here at coral reef, reef health, into the Gulf of Mexico, particularly west coast of Florida. A lot of cruises there, all the way up to the Arctic. So what are the endpoints, and how can we put together what's happening with respect to the ocean atmospheric interface, particularly with respect to carbon dioxide? Why is it important? Because most of human CO2 emitted into the atmosphere ends up, a lot of it, in the world oceans. This changes the chemistry of those oceans, and Paul alluded to it. It reduces the ability of the organisms to form shell protective shells. It changes their habitat, food web, etc. So there's a lot of issues, and we don't even begin to understand all of what's going on. But we're trying, again, to get a handle and model this at a high level for marine ecosystems, again, with partners. Here's another one that's sort of the unique USGS role, and that's with respect to natural hazards. We have the delegated responsibility for the federal government to report on earthquakes, volcanic eruptions, and landslides, and then our work in flood and severe weather supports the statutory mandates of other agencies like NOAA and EPA. So just a couple of examples. Here was the earthquake in Haiti, remember that? We looked, USGS was on the ground monitoring that, our seismic network. The reason I show it is because here's an example where an earthquake, our model here, you see vertical displacement, 1.5 meters to up, 1.5 meters down. The shore side at Port-au-Prince experienced the downside of about a meter drop that was equivalent. If you look at remember I was talking about the filling of the bathtub change in quote-unquote sea level rise. This is equivalent to about 500 million years of that change like that. So the reason I bring it up is that hazards and natural hazards around earthquakes and so forth are important with respect to sea level rise also. And just a lot of folks aren't necessarily aware of that. This is a tsunami warning index that we put together. This is the Caribbean. So again, we take these earthquake risks and so forth, move those to tsunami warning. I'm almost through. And also, the third application here is the earthquake piece, tsunami, and then landslides or potential for marine landslides. And this is just the East Coast, and seeing where former landslides have been in the future. So my last two slides, I just put together the sort of 6 big questions around this topic of stressors and ecosystem services for coastal and marine ecosystems that we, USGS, are asking ourselves as we go forward every day. And this will make, I think, a nice segue into the conversation. How can ecosystem services and their values be routinely incorporated into sustainable management decisions that, for us, Department of the Interior and partners need to make? So then, number 2, okay, what science do we need, and what level of certainty do we need around that science in order to be helpful and make us worth the investment in the science part for these decisions? And then how can the value of that science that we bring be more accurately appraised itself, not just the value of ecosystem services, but the value of science for us, return on investment for science to address those ecosystem services? And then finally, metrics, and I know this roundtable's talked a lot about metrics and meaningful metrics for appraising this. And then, again, the socioeconomic. How can we bring the social side? There's been some discussion around aesthetics and so forth. How do we bring things that traditionally have no value into a discussion? And if we're not able to do that, their value is going to remain 0. And we certainly don't want that in a discussion about ecosystem services. And then for us at Interior, adaptive management is one of the #1 tools that we use in looking at how do we learn, right? It's learn as you go, adapt on based on what you learn. So how do we bring that adaptive management approach? So that's what we're doing at USGS, and I think we then go to questions.